This was our first look at the distant universe from the Hubble Space Telescope. A blurry, failed promise. A billion-dollar catastrophe floating about 340 miles above the Earth. This is what the world saw in 1990. This is the universe as we know it today, thanks to that very same telescope. This is the story of how a team of engineers and astronauts pulled off one of the most audacious repair missions in history to save our window to the cosmos. This isn't just about a telescope. It's one of the greatest comebacks in the history of science. A story of how we fixed a flaw the width of a human hair from hundreds of miles away while traveling at 17,000 miles per hour. This is the story of the ingenious engineering that gave us the universe. For centuries, we've looked up at the stars through a shimmering, turbulent veil, our own atmosphere. It's why stars twinkle. This atmospheric distortion blurs our view, absorbing huge bands of light, especially in the ultraviolet spectrum, and blinding us to some of the universe's most energetic secrets. Astronomers dreamed of an escape, a way to put an observatory above the clouds, above the air itself, into the pure black void of space. The idea of a big space telescope wasn't new. It had been a dream since the 1940s. But turning that dream into hardware was a monumental task. The project that would become Hubble finally got going in the 1970s as a team-up between NASA and the European Space Agency. The goal was audacious. Build a telescope that could capture images with 10 times the resolution of the best observatories on the ground. It had to see the universe with a clarity never before possible, peering into the very ultraviolet light our planet blocks. The engineering challenges were immense. The telescope had to survive the violent G-forces of a shuttle launch. It had to endure the most hostile environment imaginable, cycling between scorching sunlight and the absolute cold of Earth's shadow every 95 minutes or so. And it had to do all this while staying perfectly still, able to lock onto a target with absurd precision. We're talking about the ability to hold a laser on a dime 200 miles away for 24 hours straight. This wasn't just building a telescope, it was building a precision spacecraft unlike any other. At the core of this incredible machine is the Optical Telescope Assembly, or OTA. It's Hubble's eye, and its design is a masterpiece. Hubble is a specific type of reflector called a Ritchey-Chrétien telescope. This design uses two specially shaped hyperbolic mirrors to gather and focus starlight. The main, or primary mirror, is a breathtaking 2.4 meters, or 7.9 feet across. Light from distant galaxies travels down the telescope's tube, hits this giant concave mirror, and bounces up to a much smaller 12-inch secondary mirror. That secondary mirror then shoots the light back through a hole in the main mirror where it's finally focused for the scientific instruments to analyze. The magic of the Ritchey-Chrétien design is its ability to create razor-sharp images across a wide field of view, getting rid of optical errors that can make stars at the edge of an image look like fuzzy comets. But this incredible performance comes at a price. Those hyperbolic mirrors are notoriously difficult to get right. The specs for Hubble's primary mirror were almost unbelievable. It was polished to a smoothness of within 10 nanometers. To put that in perspective, if you scaled that mirror up to be the width of the United States, the biggest bump on its surface would be less than 3 inches tall. This near perfection was critical for Hubble to be diffraction limited, meaning its sharpness would only be limited by the laws of physics, not by flaws in its own optics. The mirror was coated with a layer of pure aluminum for reflectivity, then protected by an impossibly thin layer of magnesium fluoride, which also helps it see crucial ultraviolet light. To hold this precision in the brutal environment of space, the whole optical assembly sits in a sophisticated support structure. This isn't just a tube, it's a truss made of graphite epoxy composite. You might find this advanced material in high-end tennis rackets or racing bikes. It was chosen for its incredible stiffness, low weight, and, most importantly, its near-zero expansion or contraction with temperature changes. While the outside of the telescope swings between hundreds of degrees, this frame ensures the distance between the two mirrors remains perfectly aligned. As another layer of stability, a system of heaters keeps the mirrors at a near-constant room temperature, about 70 degrees Fahrenheit, preventing even the slightest temperature change from warping their perfect shape. On April 24, 1990, the Space Shuttle Discovery lifted off, carrying Hubble into orbit. It was the climax of decades of work, billions of dollars, and the dreams of thousands. The world watched, waiting for that first, stunning look into the cosmos. And then, the first images came back. They were blurry, unfocused. While sharper than images from Earth, they were a devastating disappointment. A wave of shock and disbelief washed over NASA and the astronomy community. The world's most expensive telescope was a dud. A frantic investigation began. The diagnosis was as shocking as it was precise: spherical aberration. The primary mirror, that masterpiece of engineering, had been ground to the wrong shape. The outer edge of the mirror was too flat by a mere 2.2 microns, about a 50th of the thickness of a human hair. It was an unbelievably tiny error, but it had catastrophic consequences. Because of this flaw, light hitting the edge of the mirror focused on a different point than light from the center. The result? A fuzzy halo of light around every single star, smearing the very details Hubble was built to see. The telescope became a national embarrassment, the butt of late-night talk show jokes. The dream had become a nightmare. In face of this disaster, NASA's engineers didn't give up. They fell back on one of the brilliant parts of Hubble's original design. It was the only telescope ever designed to be serviced in orbit by astronauts. This was revolutionary. Hubble was built to be modular. Key systems were packaged into orbital replacement units, or ORUs. The whole telescope was covered in handrails and used special, oversized connectors that astronauts could handle in their bulky, pressurized suitcases. That design philosophy was about to save the entire mission. The problem was obvious. You couldn't just fly up and swap out a 2.4-meter mirror in zero gravity. The solution had to be way more clever. The engineers realized that if you can't fix the mirror, you have to fix the light coming from it. They decided to give Hubble a pair of glasses. This led to the creation of one of the brilliantly named pieces of space hardware ever, COSTAR, the Corrective Optics Space Telescope Axial Replacement. COSTAR was a device about the size of a telephone booth that held a series of small, deployable mirrors. The plan was to remove one of Hubble's other instruments and slide COSTAR into its place. Once installed, tiny robotic arms would extend 5 pairs of coin-sized mirrors right into the path of the light coming from the flawed primary mirror. Each tiny mirror was ground with the exact opposite flaw of the main mirror, canceling out the aberration and delivering a perfectly focused beam of light to Hubble's other instruments. At the same time, the main camera, the Wide Field and Planetary Camera, or WPFC, was already due for an upgrade. Its replacement, WPFC-2, was redesigned with its own internal corrective optics built right in, so it wouldn't even need COSTAR. The plan was set for a high-stakes mission to perform cosmic eye surgery. In December 1993, the Space Shuttle Endeavour launched on mission STS-61. The pressure on NASA and the 7-person astronaut crew was immense. This was set to be the most complex shuttle mission since the moon landings. It would demand a record-breaking 5 consecutive days of spacewalks to perform a series of grueling, high-precision tasks. The astronauts trained for hundreds of hours in underwater labs, rehearsing every move, every turn of a bolt. They developed over 100 new tools just for this mission, all designed to be used with the thick, clumsy gloves of a spacesuit. Once in orbit, they snagged Hubble with the shuttle's robotic arm and secured it in the cargo bay. For 5 straight days, pairs of astronauts ventured out. Their work was a ballet of human skill and robotic precision. They carefully pulled out the old wide-field and planetary camera and slid the new, corrected WFPC-2 into its place. Then came the trickiest part. Astronauts Catherine Thornton and Thomas Akers worked to remove the high-speed photometer and install CoStar. Imagine guiding an instrument the size of a phone booth into a tight slot with less than an inch of clearance, all while floating in space. The astronauts also replaced Hubble's solar arrays, which had been causing a slight jitter, and upgraded failed gyroscopes needed for pointing the telescope. After more than 35 hours of spacewalks, the job was done. The astronauts released Hubble back into orbit and came home. Now, the world held its breath. Back on Earth, the team at the Space Telescope Science Institute pointed the newly repaired observatory at a star and took a picture. The relief was instantaneous. The images were perfect, crystal clear. The fuzzy blobs were gone, replaced by pin-sharp points of light. The before and after pictures became legendary, a stunning testament to the mission's success. Hubble wasn't just fixed, it was better than anyone had ever dreamed. The floodgates of discovery blew open. With its vision corrected, Hubble began to revolutionize nearly every field of astronomy. It captured the iconic pillars of creation, a stellar nursery of gas and dust where new stars are born. Its deep field images, where the telescope stared at a tiny, seemingly empty patch of sky for days, revealed thousands of galaxies stretching back to the dawn of time, completely changing our understanding of the cosmos. Hubble's precise measurements of distant supernovae proved that the universe's expansion is accelerating, a Nobel Prize-winning discovery that led to the theory of dark energy. It gave us definitive proof of supermassive black holes at the center of galaxies and was the first telescope to analyze the atmosphere of a planet outside our solar system. The comeback was complete. The telescope that was once a symbol of failure had become one of humanity's greatest scientific triumphs. That incredible first servicing mission was just the beginning. The modular design that allowed for the initial repair also meant Hubble could be upgraded. Over the next 16 years, 4 more shuttle crews would visit the telescope in 1997, 1999, 2002, and 2009. These missions turned Hubble into a completely new machine again and again. During servicing Mission 2, astronauts installed 2 new instruments that extended Hubble's vision into the infrared spectrum for the first time. Servicing Mission 3A was an emergency repair to replace all 6 of the telescope's gyroscopes and its main computer, which got a processor 20 times faster than the original. During servicing Mission 3B, astronauts installed the Advanced Camera for Surveys, which boosted Hubble's imaging power by 10 times and replaced the old solar arrays with smaller, more efficient ones that increased its power by 30%. The final mission in 2009 was maybe the most ambitious. Astronauts installed 2 brand-new, state-of-the-art instruments and even performed surgery on instruments that were never designed to be fixed in space, opening them up to replace fried circuit boards. By the time the shuttle Atlantis left for the last time, every single one of Hubble's original scientific instruments had been replaced. CoStar, its job long done since all the new instruments had their own built-in corrections, was removed and is now on display at the Smithsonian. The Hubble of 2009 was exponentially more powerful than the one launched in 1990, a shining example of its brilliant serviceable design. This ongoing cycle of repair and improvement is what makes the Hubble story so powerful. It's a masterclass in engineering foresight and human ingenuity. If you find stories like this as fascinating as we do, make sure to subscribe so you don't miss our next exploration of science and technology. And we have to ask, what's your favorite Hubble image? Let us know in the comments below. Today, more than 30 years after its troubled launch, the Hubble Space Telescope is still going strong. It has become more than just a satellite, it's a cultural icon. Its images of nebulas and galaxies haven't just rewritten textbooks, they've become part of our shared visual language for the cosmos. Hubble has brought the scale, beauty, and sheer wonder of the universe into our lives in a way no other instrument ever has. Its engineering legacy is just as profound. The lessons learned from Hubble's modular design have fundamentally shaped how we build complex machines for space. Its success directly informed the design of its successor, the James Webb Telescope, and continues to influence plans for future observatories. The story of Hubble is the ultimate comeback story. It's about a brilliant dream, a near-total failure, and an incredible redemption. It proves that our greatest achievements are often born not from getting everything right the first time, but from our ability to face our mistakes, innovate under pressure, and work together to solve the impossible. Hubble isn't just a window to the universe, it's a mirror, reflecting the very best of our curiosity, resilience, and ingenuity.